Good morning, one and all. My name is V. Abhijit Kumar. My roll number is 24951A6602. I'm studying in CSC AIML, that is Computer Science and Engineering, with the specification of Artificial Intelligence and Machine Learning, third semester, BTech second year, Institute of Aeronautical Engineering. In this AAT Tech Talk of the subject of Probability and Statistics, I'm going to explain about the topic of Maximal Correlation Regression. Now let's go through the contents. In the first place, I'm going to introduce the topic to you, where the foundation of what MCR is, or else what maximal correlation regression is. I'm going to explain it over there, and after that I'm going to explain why this is useful. I'm going to explain the limitations of simple correlation over there, and after that HGR maximal correlation. I'm going to introduce the mathematical foundation of this topic over there, which is actually found by Hurstfeld, Gabelin, Rennie. And after that, I'm going to explain about ACE method or institution method, where I'm going to explain about the practical algorithm for finding transformations. And after that, MCR pipeline. I'm going to show the step-by-step process of applying the method over there. And after that, practical considerations. I'm going to highlight the real world challenges like sample size, outliners, etc. over there. And after that, I'm going to show the case study with an example of actual data. And after that, I'm going to explain about the best practices and cautions, where I'm going to provide guidelines and warnings to avoid misuse. And after that, finally, I'm going to conclude the topic, where I'm going to summarize everything. Introduction. This maximal correlation regression, it is actually an advanced idea built on the simple concept of correlation. Normal correlation means it only measures linear or straight line relationships. But in real life, data often follows non-linear patterns like waves, curves, or cycles. Hence, maximal correlation regression extends basic correlation ideas. And it solves this by transforming the variables, that is, applying mathematical functions like squaring, taking a log, or using a sine or cosine so that the hidden structures become visible. Once the data is transformed appropriately, even the simple linear regression can model the relationship efficiently and effectively. Hence, it helps us detect non-linear relationships between the variables. We transform the variables so hidden patterns become visible, and after the transformation, most importantly, we can use simple linear regression efficiently. So this MCR connects the concepts of correlation, regression, and transformation. It's, it acts as a bridge between these three concepts, allowing us to uncover patterns that basic methods would miss in a lot of scenarios. Explain why this is useful. See, basically, simple correlation or traditional correlation fails when relationships are non-linear. It misses non-linear relationships like curves, waves, etc. For example, if y is equal to x square, Pearson's correlation may suggest almost no relationship, even more, even though y clearly depends on x. MCR is useful because it detects non-linear relationships which are hidden by transforming variables. It keeps models simple and interpretable instead of turning to very complex black box methods. It is helpful when nonlinear regression performs poorly at first glance. It is widely applicable in economics or any other aspects where non-linear demand is applicable, engineering where signal patterns are applicable, and data science where complex dependencies are applicable. In short, it extends the usefulness of simple tools by giving them the power to capture nonlinear structures. Hence, by transforming variables, we can find stronger patterns. It helps keep models simple and easy to interpret. Hence, this is the reason why this is useful. Now let's go through to the next slide. Now let's go through HGR maximal correlation. This concept comes from Hirschfeld, Gabelin, and Renyi. H is for Hirschfeld, G is for Gabelin, and R is for Renyi. The goal is to find functions f of x and g of y that make the correlation between them as strong as possible. To be fair, we must normalize them, means the mean is equal to 0 and variance is equal to 1. To be fair, and the maximum possible correlation is called rho star. Rho star ranges from 0 to 1. At 0, x and y are independent, where no relationship is of existence even after the transformation, and at 1, perfect dependence occurs after transformation. This generalizes Pearson correlation to nonlinear settings. Talk about the ACE method. The ACE method, ACE, alternating conditional expectations. It is a practical algorithm for finding f of x and g of y. It works like this. First of all, we have to start with an initial guess for g of y, and given g of y, estimate the best of f of x. Given g of x, given f of x, update g of y. We have to repeat these steps until things stop changing much. This process is called convergence. At each step, the functions are normalized to make things meaningful, to make results meaningful. Basically, the idea is like two people taking turns adjusting their positions until both are perfectly aligned. This iterative adjustment process allows the algorithm to uncover the nonlinear relationships hidden in the data. Let's go through the practical workflow of applying MCR. MCR pipeline. First step is to use ACE or any similar method to ACE to find the best transformations for f of x and g of y. Step 2 is to run a simple linear regression on these transformed variables. Step 3, we have to validate the model to make sure that the patterns are real and not random. And step 4, we have to adjust the transformations if overfitting occurs. We have to adjust them by simplifying if the model overfits or too tailored to the data. The essence of this entire pipeline is that MCR is equal to transformation plus linear regression. It basically gives us the power of nonlinear modeling but keeps the interpretability of linear regression. Hence, this is the practical workflow of applying MCR. Now let's go through the practical considerations. In practice, generally several challenges arise. The first challenge is sample size. More flexible transformations need more data, otherwise we might see patterns are not real. And the second challenge is cross validation. Cross validation or splitting the data into training and tests sets it's vital for checking reliability of results. And after that, the outliers. The outliers can distort correlations or the extreme points. They can distort correlations. So they must be handled carefully with a lot of concern. And after that, the smoothness and interpretability. The transformations over there should not be overly complicated. They should remain smooth and interpretable. A smoother transformation is easier to explain and trust. And finally, visualization. We have to always visualize the results to confirm patterns are real. We have to always visualize that the graph transformations and residuals to confirm the patterns are meaningful. Hence, these considerations help us avoid misinterpretation and false confidence. Let's take a case study. Suppose y is equal to sin x plus some noise. If we try simple linear regression between x and y, the correlation looks very weak. The direct linear regression gives very low correlation because the true relationship is wave-like. If we transform x with sine, suddenly the relationship becomes obvious and it reveals strong dependence. After transformation, the regression, it explains the y, most of the variation in y. Hence, this demonstrates how MCR uncovers the hidden relationships that normal methods fail to capture. It shows beginners the exact value of using transformation in any kind of regression. Now let's go through some best practices and cautions. These are some guidelines for using MCR wisely. First of all, we have to start simple. We have to try ACE with smoothing before going for complex methods. We have to always cross-validate and inspect both transformations and residuals. We have to avoid over-interpretation just because a transformation, it looks interesting, that doesn't mean it's meaningful. This reminds us that MCR is a tool for discovery and not a guaranteed truth. Human expertise is essential to make to make sense of the results. The maximal correlation regression MCR. It is a practical and systematic approach for extending the power of linear models to nonlinear settings. It helps uncover hidden linear structures in data that may first appear complex or nonlinear, but by applying suitable methods to the transformations, MCR allows us to retain the simplicity and interpretability of linear regression while still capturing richer and more complex relationships. Maximal correlation regression or MCR, it focuses on finding the right transformations of variables so that the hidden data structures become visible. What may look like a complex or non-linear relationship can often be reshaped into something simple once the correct transformation is applied. It is powerful because it allows us to uncover the models that are both simple and interpretable even the even when the original data appears to follow nonlinear patterns. Instead of relying on black box methods, MCR shows how thoughtful transformations combined with linear regression can explain the data directly and clearly. And at the same time, the reliable use of MCR depends on careful practice. Transformations should be smoothed to avoid overfitting. The results must always be validated through methods like cross-validation and domain knowledge is needed to interpret the meaning of the discovered patterns. These precautions ensure that the insights we gain are trustworthy and genuinely reflect the underlying data relationships. Hence, this is the conclusion. And finally, I would like to sincerely thank my respected professors who had given me this wonderful opportunity to speak on this topic.